Welcome. In this video, we are going to discuss about the inference concerning proportions. So till now, what we have dealt is that we have considered some inference concerning a mean or two means, variance, two variance. These were the things that we were considered. Okay. Here, what we are going to do is that we are going to consider a large population. Okay. From this population is divided into two things, not necessarily that this should be divided equally. Okay, basically the entire population we are going to divide into two things. One is having some attribute. Okay, it is having some property. Okay, the other thing is of course does not have that property whatsoever, the property that we are discussing. Okay, for example, if you consider a class of okay, consider some class of students. Okay, so out of which we may be interested only in boys students. Okay, only boys or girls. So the entire class is now divided into two categories as of now. Okay, so that is the one is boys. Okay, the other is not boys. Okay, this may be the case. So when I say not boys, it may be girls or transgenders as well, right? So the attribute here, attribute means having some property. Okay, so this is the thing that we are considering. Okay, so classified into two types. One is having the attribute and the members not having that attribute. And now in the entire population, only certain set of samples, certain set of members of the population have that attribute. So we'll have to calculate the proportion of it. Okay, that proportion we denote it as P, and the proportion of elements not having the attribute we denote it as Q. Here this P is the parameter upon which we are going to do all the calculations. This P may be called as proportion or percentage or probability that the members have the attribute that we are dealing with. Okay, so again here we will take a random sample of size n. Okay, from the population, and x is the number of elements in the sample having the attribute. So from an entire population, if we are trying to identify the average height of a students, that may be our experiment. Okay, so in order to do it, among all the students we just divide the population into two categories, that is boys and other people. Okay, among the boys we take some sample. Okay, that may be the case, or from a whole thing we will take a sample and examine whether that is the thing happening or not. Okay, and here the sample proportion, as I told you here, this P is the parameter upon which we do the testing and all. So we must have some statistics, that is x upon n. Okay, if we notice this x is a binomial random variable, okay, with parameters n and p, and when n is large, of course we convert it into the standard normal variate using this one. Okay, so here we should be very careful how large should our n be. Okay, if we need to convert it to a standard normal variable. Okay, and of course if we do some simple calculations into it. Okay, if we divide the whole thing by n and multiply by n, so that is, this is the case. Okay, this becomes x upon n minus p upon n, and it goes inside and we get npq upon n squared. So 1 n and n gets cancelled. So what we have is x upon n, sorry, np, right? It was np. So minus p upon under root pq upon n. So this is the standard normal variate that we have, right? Okay, moving further. So this is the hypothesis test concerning one proportion. So we are going to test the proportion equals something or not. Okay, and of course here we have made a question mark that sample size is large enough. what are we going to do? That we will see when we deal with the problems. Okay, and the test statistic is x upon n minus p naught upon under root p naught times of 1 minus p naught upon n. This is the test statistics. If this is the null hypothesis, of course the alternate we will have either greater than or less than or simply not equal to. So just like we had in the previous test, here also we have the cases upon which we reject the null hypothesis. Okay, and moving further, here we have an example. A standard drug is known to be effective in about 80 percentage of the cases. So in 80 percentage of the cases, it is known to be effective, right? When it is used to treat infections. A new drug is found to be effective in 104 out of 120 cases tried. Okay, is the superiority of the drug well established at 0.05 level of significance? So here, this of course, by looking at this problem, we might have identified that our H naught is going to be P equals something, and H1 that we'll have to decide uh, P greater than P naught or less than P naught or not equal to P naught. Here, the question is the superiority of the drug well established? So, which means greater than. Okay, superiority means whether it is established or not. Okay, in general, we take the H naught to be P equals P naught, and what is the P naught here? It is given that 80 percentage is there. Okay, so this is our H naught and this is our H1. Okay, now that we need to identify the value of what? Okay, so this value P naught is known, that is 0.80. Okay, in the test statistic we will have to substitute x upon n, and x is the number of members having the attribute, right? And n is the size of the sample. So in this question, we have tested it for 120 cases. So n is 120 and x, out of which for 104 people it was effective. So we divide the group into two categories, that the drug is effective to this people and the drug is not effective to the people. So x is 104. We just substitute these values into it. So basically our test statistic would give us what? 104 upon 120 minus zero point 0.8 divided by under root zero point 0.8 times of 1 minus zero point 0.8 upon 120. When we simplify it, we get z to be 1.826. Okay, from the table for 0.05, we calculate z alpha to be this one, and here we notice that our calculated value of z is bigger than the table value, therefore we reject with this thing. So this is the case here. So we reject the null hypothesis, right? So by rejecting, what do we conclude is that, so when we reject the null hypothesis, the superiority of the drug is considered, is well established at the specified level of significance. Moving further, here in this problem we have a random sample of 600 cars making a right turn at intersection. Okay, out of which 157 cars pulled into the wrong lane. Okay, and we'll have to test the null hypothesis that actually 30 percentage of the car, 30 percentage of all drivers make this mistake at the given intersection. Okay, and we are asked to use the null hypothesis that p not equals 30 and the level of significance is 0.05. Okay, here this 157 pulled into the wrong lane. So here we are interested in pulling into the wrong lane. Okay, so of course x is 157. Okay, and n is 600 cars. Okay, so here the attribute that we are interested is pulling into the wrong lane, right? and this proportion we'll have to calculate and substitute at this place. Okay, and p is given like p naught is given to be 0.30 in the question itself. So the null hypothesis and the alternate are clear. We just substitute the given values into it, and we see that uh, actually this should be minus 2.05. Okay, so basically if you see, the calculation would be 157 upon 600 minus zero point 0.3 divided by under root zero point 0.3 times of zero point 0.7 upon 600. This will give you minus 2.05. Okay, so if you compare absolute of z with your z alpha upon 2, this one is bigger. So we reject the null hypothesis. So by rejecting the null hypothesis, we'll have to accept the alternate hypothesis that this proportion is not 30 percentage. Okay. And moving further, here we have the ideologies to calculate the confidence interval for this proportion. So basically, here if you see, this is the general case. Okay, case 1 and 2 are the one-sided ones. Okay, case 3 is the generalized one. So if absolute of z is smaller than or equal to z alpha upon 2, we accept the null hypothesis, isn't it? So basically this is the region of acceptance. So if you open it, you would get a minus z alpha upon 2 less than z less than z alpha upon 2. Okay, so if this is the region of acceptance, whatever is outside this is the region of rejection. Okay, that is specified in the critical region calculation. Okay, so this region of acceptance we just elaborate here. So what was it? Minus z alpha upon 2 smaller than or equals z. Okay, since it is continuous, it's completely fine to omit the equality. So this was the case. And what was our z? It was x upon n minus p naught upon under root p naught times of 1 minus p naught upon n. This was the thing. Okay, so supposing this one we are taking it as p, and this one we have it as x upon n. So and this is what we have it, right? So now you just take other things to the other sides. Okay, so this was the thing that we have. Okay, so from here I am writing. So if you see, minus z alpha upon 2 multiplied with x upon n 1 minus x upon n divided by n less than p minus x upon n less than z alpha upon 2 product with under root x upon n times of 1 minus x upon n divided by n. And if you take this quantity to the like if you just add x upon n to the entire equation, you will get back to this. So this is how we calculate the confidence interval. Okay, and hopefully you can do these problems. So let me not explain it in detail, but still 36 out of 100 senior citizen are found to be diabetic. So here the attribute that we are interested is being diabetic. Okay, we are asked to calculate the 95% confidence interval for this true population. So here n is your 100, x is 36. Okay, and we know the confidence that level of significance is specified, so with which we calculate everything, and we just substitute all the things into the expression, and finally we get the confidence interval as like this. Okay, in the second example, we have 200 industrial accidents. Okay, we are taking a random sample of 200 industrial accidents, out of which it was found that 116 were due to unsafe working conditions. Here, the attribute that we are interested in is unsafe working conditions, and we are asked to construct the 99% confidence interval. If we just substitute all the values into the expression of for finding the confidence interval, we get the confidence interval as like this. Okay, so here in this problem it is given that a random sample of 500 apples was taken from a large consignment and 65 were found to be bad. We are asked to estimate the proportion of bad apples in the consignment and the standard error of the estimate. Okay, so first of all, here n is what? N is 500, isn't it? And the attribute that we are interested is the bad apples being bad, that is 65. And alpha is not specified, so we just take it to be 0.01. Okay, let us take it this way. So z alpha upon 2, from the table it is 2.575. Okay, now let us find out 99 percentage confidence interval. Okay, it is x upon n, right? So 65 upon 500 minus z alpha upon 2 product with x upon n multiplied with 1 minus x upon n divided by n, which is less than p, which is less than 65 upon 500 plus z alpha upon 2 product with 65 upon 500 multiplied with 1 minus 65 upon 500 divided by 500. Okay, and when you make the calculation and simplify it, you would get it as 0.1261 less than p less than 0.1339. So this is the thing that we will have. And remember, here if you see, everywhere this interval was like the value was smaller than 1 and bigger than 0. Since it is a proportion, we should have the final answer in this form only. That is, like in general, this proportion p should lie between 0 to 1 only. Okay, it can include a 0 and 1, but that will not happen in general. Okay, so basically this p should be in this interval. Okay, and the estimate that we are going to take would be in some e, which is a subset of this interval. Mathematically speaking, this would be the case. Okay, here we are asked to find out. Okay, here we are discussing about the maximum error. Okay, so this could be the maximum error. It is that upon z alpha upon 2 upon sorry multiplied with this quantity. Okay, in a random sample of 200 industrial accidents, it was found that due to unsafe working conditions. Okay, what can we say about the maximum error with 99% confidence? Okay, if we use the sample proportion as the point estimate of true proportion, here all we need to do is that we have n, x is there, alpha upon 2 is there. So whatever we have done here, the same thing you will have to calculate this value, and this would be the error that is required. Okay, and if you calculate it here, you would have your e to be 0.065. Oh, sorry, it would be a 0.21396, right? And moving further, here among 100 fish caught, 18 were inedible due to the pollution in environment. So here we are interested in the attribute that it is inedible to eat. Okay, if we use this sample proportion as an estimate of corresponding true population, with what confidence we can assert that the maximum error is 0.065? So it is clearly given that error is this quantity, and we are asked to calculate the value of alpha from this. Okay, so let me tell you the idea. So E is known, N is known, X is known, right? So that is E is what? Z alpha upon, okay, that is also here, right? If we just substitute all these things here, it is 0.065 equals Z alpha upon 2 multiplied with 18 upon 100 product with 1 minus 18 upon 100 whole divided by 100. Okay, and if you simplify, you would get Z alpha upon 2 is 1 upon 69. So what from this, if you just go to your standard normal table and see the, like, from there you read the value of alpha upon 2, and from which you can very well calculate this 1 minus alpha. Okay, so here you just need to calculate the z alpha upon 2 and go to your standard normal table, and from there read the value of alpha, and that's it. Okay, and if maximum error is given, if we are asked to find out the sample size required, which can be estimated through this one. Okay, here the question is, what is the sample size required to estimate an unknown proportion with the maximum error, right? So it is what? N is 1 upon 4 times of, which is 1.96 upon error is 0.06 whole square. If you just calculate, you would get it as approximately 267 with probability 95 percentage.